So, welcome to everybody. Happy New Year, first of all. I wish you a lot of success, particularly, of course, for nonlinear optics. What I would like to do today, well, I'm sorry that I have to speak to an empty classroom here again, but you know, the situation is as it is, and well, so I speak into the cloud, I guess. So, nevertheless, what I want to do today is the following. I want to talk about the susceptibility in a very brief manner. If you look into the script, then you see that I have several chapters there, and ideally I would like to cover all these 3 or 4 chapters today. Maybe this lecture is a little bit longer, and maybe I don't finish it such that we have to continue it next Monday. Let's see how far we can go today. I would like to start with a few remarks on the susceptibility tensor, in particular also making remarks about response functions. If you think about the susceptibility, then it's a response function. Let me try to explain that and write a few things. So what we usually, what we did from the beginning, polarization as the effect of some cause, which usually is the electric field. So the laser produces an electric field. This falls on some material, creates a polarization. So the polarization is the effect, and the light field, the electric field of the laser, is the cause. Yeah? So, and therefore, what we most of the time do is that we just write that the polarization, I write here the ETH component, that this is equal to epsilon 0 times the susceptibility tensor. In the case of a linear interaction, it's just has just 2 indices, so it can be represented by a matrix. So we have this thing here, right? And what we actually mean is something more complicated, namely, in the most general case, we have to be aware that all the polarization that we measure at this instant can be created by everything in the past. So, and if you speak about a linear interaction, then you would say what we measure, the polarization that we measure today, so at t equal to 0, is a linear combination of all the instants in the past. And because it's continuous, we don't write this linear combination as discrete terms, but we write it as an integral. So we write this thing here, but we mean actually something more complicated, namely pi of t is equal to epsilon 0 times, and now an integral, I write it here from tau equals to minus infinity to plus infinity, but I don't mean this entirely serious. I'll come to that in a second. And now we integrate over this tau. Yeah, so we integrate over all these different times. And so we have the susceptibility tensor here at different times. Yeah, so first order susceptibility in the case of linear interaction, and then the electric field at these different times. Yeah? So this is what's called the most general linear relationship. Yeah? So the most general linear relationship between some cause, namely the electric field, and the effect, namely the polarization. Actually, this Yeah, this relationship is already a little bit too general because it is clear that the polarization now and today can't depend on the electric field tomorrow. So therefore we won't integrate, so we actually would integrate from tau equal to 0 to infinity. Yeah? So because then we go into, so for positive taus, we go in the past for the electric field. Okay, well, if you look at this most general linear relationship, then you realize, of course, that it's a convolution. So in German, it's a Faltung. Yeah? So let's write that down. I would give it a number here, these equations, such that I can reference it. So equation 2 says that P is the Faltung or convolution of chi and the electric field. In other words, or in symbols, so P, the linear polarization, this would be written as epsilon 0 times chi ij of t. And then Faltung, the symbol is the star, and we would have Ej times t. And if we speak about Faltung or convolution, then we have the Faltungstheorem or convolutions theorem, which I would use next. So the Faltungstheorem, namely that P, if we do the Fourier transform, then we can write this star just as a product, but now in frequency space. So I have now the polarization as a function of frequency, and epsilon 0 times chi ij, first order, also as a function of the frequency. So this susceptibility is now the Fourier transform of the susceptibility in time domain. So and instead of this star, we just have the product Ij as a function of the frequency. And this thing is, as I said, the Fourier transform. So it is just the same thing, time domain times e to the I minus I omega tau integrated over tau. Yeah? So that's for the linear case. Once again, the interesting point here is that we consider susceptibility as a response. Yeah? So a response means that we ask a question and we get an answer, or in other terms, that we have a cause, and so the cause is, so to say, the question, and we have an effect, that's the answer. Yeah, so once again, this here is the effect, and this here is the cause. And we said that we model it mathematically by a linear combination of all the events in the past. Now the question is what we do in the nonlinear case, and to keep it reasonably simple, we just look at the quadratic case. So what we want to establish now would be the most general quadratic relation for a response function. So let's write that down. So the most general quadratic relation. Well, not very surprisingly, we have two electric fields. So and two integrals. Because we have two electric fields, then of course the effect can, the polarization today can be dependent on one field yesterday and the other field the day before yesterday. In principle, that's possible, right? And so we have to account for that. So we integrate over tau from minus infinity to plus infinity. In reality, it is just from 0 to infinity for both fields, and we integrate, of course, over both times. And now the susceptibility looks a little bit more complicated. It has, of course, two arguments, and as I said, two electric fields. IJK, EK tau t minus tau 2, right? So you see that what we introduce kind of through, well, physics arguments can actually be formulated entirely without talking about electric field susceptibilities and polarization, but it can be discussed in a more abstract way. We just have a cause and we have an effect, and there's something in between. We call it susceptibility. In the abstract language, it is the response function, and this response function is in the linear case, just a linear combination, and here it's a quadratic combination. So you see that this is a very general framework. The only physics that we put in so far is, well, actually the only physics that we put in at all is that we say that we request causality. Yeah? So that we say that the effect of today can't depend on a cause tomorrow. Of course, in the nonlinear case, everything looks a little bit more complicated, and this is even true if we just go to the frequency domain here. Just let me write that down. So in frequency domain, one would need to do a Fourier transform, and we get now the second order polarization. Yeah, so you see the immediate connection to nonlinear optics. So we have now the second order nonlinear polarization. If you look above here, right, it's just a multiplication of the susceptibility and the electric field, both in frequency domain, of course. Here one integral remains, in general at least. So we have the susceptibility now in frequency domain, and it's written in this kind of a special way. Yeah, so we write actually 3 arguments, although 2 arguments would be sufficient. Yeah? So the arguments that are sufficient in principle are F1 and F2. So the 2 frequencies of these electric fields, but we write their sum also, so F3 here, in order to make it clear. And this semicolon, in contrast to the colons here, this signifies the special role of this first argument. So there's something missing still, of course, namely Ej of F1 and Ek of F2. right? Yeah, and this susceptibility here, this is defined. Yeah, so this chi 2 ijk, this we would get by integration over tau 1 and tau 2 of chi I jk tau 1 and tau 2. Yeah, so kind of the Fourier transform. Tau 2 I to the minus I omega 2 tau 2. Yeah, and in the monochromatic case, actually, this integration here, yeah, that is a little bit, yeah, not so nice. In the monochromatic case, this integration disappears. More details can be found in the script on that. So let me come to the next point here right away. So what I want to talk about is something that I announced actually already in the very first lecture, where we discussed yeah, the physics origin of the susceptibility. You certainly remember that we discussed the Lorentz model, and I would like to just give you a reminder and just show a few slides that I've shown already. Yeah, so we said that we think about the polarization as something that roots in a harmonic oscillator, in a driven damped harmonic oscillator. And then we solved this differential equation, which is easy enough, right? And we found an expression for the susceptibility, right? Yeah, so maybe you try to remember at least the structure of the susceptibility, because what I'm going to do is, of course, to make this linear oscillator, this harmonic oscillator, to make it unharmonic by introducing nonlinearities. So let us see how this works. So I want to set up an unharmonic oscillator. So we start with the ordinary differential equation of a harmonic oscillator, and then we make it unharmonic. Right? If you look at it, you find that the restoring force can be written in this way. And now for the unharmonic oscillator, we add, instead of this linear term, we add quadratic and cubic terms. Well, so far it's a free harmonic oscillator. No, it's a free unharmonic oscillator here now. It's damped already, but now we also drive it. So therefore, we also include a driver to this differential equation. A few, well, obvious assumptions. So we assume weak damping, meaning that this gamma is sufficiently small. We also remark that quite often this quadratic term actually disappears, and this corresponds to situations that that I frequently mentioned and that I will mention today again, namely that materials that have an inversion symmetry, for these materials A prime is equal to 0. So they don't show any second order effects. Okay, so we have this differential equation actually in position, but we are interested, of course, in the polarization. But it is, of course, very easy to get the polarization we just need to multiply it with the number of oscillators per volume and with the charge. Then we have the polarization. And of course, we can also write down the derivatives. Okay, yeah, and then this differential equation, so this equation 3, becomes this equation, which is the one with which we have to deal now. So we introduce a few abbreviations, actually a pretty big one, right? So we actually take the entire right-hand side of the differential equation and we write it as S of t, as some function dependent on time, right? Then this equation looks like this here. And it looks just like the differential equation with which we started. This looks like the driven harmonic oscillator. But the trick is, of course, that we disguised the polarization here, yeah, so that it's hidden in S of t, right? So the nonlinearity is was just hidden, but it's in fact still there, right? So S of t not only depends on the electric field, but it also depends on the polarization. So on the terms that we have on the right-hand side. But nevertheless, the idea kind is that we say that in leading order, right, this S of t is, well, this S of t is almost the electric field times Q divided by M. And this already gives you an idea on what we want to do. So we want to try an iterative solution. So in order to do that, we solve this differential equation with a little bit more powerful mathematics. So we do the Fourier transform of this differential equation, and we can integrate the left-hand side in parts. Right? So if we integrate that, then we find that it's equal to, well, the Fourier transform of the polarization. So we have now the polarization in frequency space, whereas as here it was still, of course, in time domain. And on the right-hand side, we have just the Fourier transform of S of t, so S of f. Right? Well, you recognize this term, of course. Yeah? So I told you to remember or try to remember the structure of the term that we had for the susceptibility for the linear case, for the Lorentz model, and well, this was there. Yeah. So and here this is just repeated, right? It is clear that this thing has to do something with the susceptibility. We saw it already. And it's a good sign that this relationship actually holds, which we have identified as the consequence of the fact that physical quantities are real quantities. Okay, back to the problem that we want to solve. So you see that we have this relationship in equation 11. And now we apply the convolution theorem. So we go back to the time domain. And then we find that the polarization is given as, well, the convolution of this thing, which in leading order is the electric field, and this term here, so Q of tau, which is basically the susceptibility. So you find the very thing that I introduced when we were discussing response function. Yeah? Here the thing is actually a little bit more complicated. Yeah? It's kind of this formal solution to our differential equation, yeah, to this differential equation 7. However, it's only an implicit solution because S still contains P. But nevertheless, at least formally, it is some progress, or looks like some progress. Okay, well, one thing to say is that this Q of t, the susceptibility can be computed. This is a little bit, you need a little bit of complex integration. And then you find that Q of t is this expression, well, which is perhaps at the moment not so important. The important thing is that for t equal smaller than 0, it is identical to 0, which again reflects what we discussed, namely that an effect today can't depend on some cause tomorrow. So what we have reproduced here is causality. Yeah, so quite good. Well, we write down this formal solution. Yeah, so we have here this equation 12. But now I substitute the original expression for S of t into it. And let me just show what S of t, how it was defined on the previous slide. Yeah, so this was this equation 6. Yeah, and I substitute this equation 6 down here. Well, and then we get this ugly expression here, right, for the polarization. And you see what we remarked several times, so that this solution for the polarization depends on the polarization. So it's an implicit solution. Not very useful, at least for the time being. So it is an implicit equation, and we now solve 15 by plugging 15 into 15. Sounds a little bit funny, but this is actually what we do approximately. And this works because the leading term of the right-hand side doesn't contain P. Okay, so before doing that, I would like to get an explicit expression for, so we have here P of t, but what I need to plug in is P of t minus tau. So I replace here tau with tau prime, and t I replace with t minus tau. Right? And then we get this thing. Right? So I just renamed variables. Nothing has happened. But now we insert 16, which is basically the same than 15. Now we replace, or we plug 16 into 15. Yeah? So when I said here, we solve 15 by plugging 15 into 15, then it's actually exactly what we do now. Right? And when we do that, then you see that we get this term here, which is independent of P, right? And for this one here, for P squared, I have to plug in this thing here, squared, right? Doesn't look nice, but, well, that's nonlinear optics, right? But you see that we have now a term that represents the linear thing, and we have a term that represents the quadratic response. We were too lazy to also write down this one here, right? But that would be straightforward. So we identify these two things, right? And you see that here. So we have now the second order polarization. Yeah. Again, you see that this Q must essentially be the susceptibility, but actually it goes here a bit further. So what we do is that we go back to frequency domain. So we write first order polarization as a convolution, right? And we now see the direct consequence, or the how both are related. And if you remember what Q was, then you find that we now have here exactly the same thing than we had in the Lorentz model in the first lecture that I gave, well, more than a month ago, 2 months ago, right? So that's reassuring. So to recover the Lorentz model here. So that was too quick. Okay, now we can do the same thing for the second order polarization. And of course, it looks more ugly. But if you look at nonlinear response functions, then you see also, so you also see this mirrored here. And with a few variable changes, we can write it in this way, such that we find here the second order susceptibility, and we actually find an expression for that, right? And this expression now is a very interesting one, because what you see is that in the second order susceptibility, we have, well, the essential terms of first order susceptibility. So what you see is that obviously second order susceptibility and first order susceptibility, that they are kind of connected, at least what concerns their, well, time dependent or frequency dependent terms, right? So, of course, there's still this prefactor A, but you see that first order and second order susceptibility, and actually also higher order susceptibilities, that they are related. And this is actually the essence of Miller's rule. Yeah, so Miller's rule says that, that both are connected. And it actually says, or it actually gives you a good kind of idea which materials are promising if you are looking for nonlinear material, right? If you have a strong susceptibility, a strong first order susceptibility, then also the second order, the nonlinear susceptibility, can be expected to be large, right? And this can be shown in quite simply. So I don't want to go through all of that. So the essence is that it says that a material with high refractive index should have large nonlinear susceptibilities, right? And of course, it's only a guide. Because you also saw that we still have this factor A here, which depends on the material. And if you want to do it precisely, then we can't do it classically, of course. We would have to do it quantum mechanically. And what you would find there would be quantum expressions, matrix elements. Okay, so here is Robert C. Miller. Yeah, I found his obituary. Yeah, so when he died, there was an announcement in some newspaper, and it's actually interesting what they wrote about him. Yeah, so it was apparently his family who wrote some pretty long text. so he, so if you look at his birthday or birth dates, then you can imagine that the Second World War affected him. So he was a soldier. He was drafted after 1 year in college, and then he fought in Europe in the Battle of the Bulge, and that's kind of that kind of touched me, because an old friend of mine who died meanwhile, he also fought in that battle, but on the wrong side. He was on the right side of the of history. And survived it. So quitted the army after the war and continued his studies. And after his PhD, he joined the Bell Labs. And the other story I liked to read was that in the morning when he went to his research institute, the Bell Labs, he would tell his children that he is going to play. So he apparently enjoyed very much what he did, and he made a few important contributions to nonlinear optics. So Miller's rule, of course, in his PhD, so already before he joined Bell Labs, he designed an instrument that was selected for an exhibition in the Smithsonian Museum. So he built the first optical parametric oscillator, and also contributed to the first quantum well laser. So quite an important person, I would say. It's interesting that that it's a little bit difficult to find information about this this physicist. Well, we can of course use this form that we found in order to find specific expressions for various nonlinear processes that we looked at, namely some frequency generation, right? Then we would get this expression here. So this C1, this contains all the quantum mechanics, so to say. Right? So this would be connected to A, to this variable A that we introduced. Then for difference frequency generation, we find this expression here, and we can also do it for second harmonic generation and for optical rectification. And if you do it quantum mechanically, the only thing that changes is that you get specific expressions here for these constants, C1 to C4. Okay, so this concludes this chapter on the anharmonic oscillator model. So this gives you an idea that the Lorentz model that we introduced, that this really has also significance if we do nonlinear optics. So this kind of simple picture of looking at interactions with an oscillator model, driven oscillator model, this actually holds. Good. So the next point would be to look at some symmetry properties. So 7.3, symmetry properties for the susceptibility tensor. And there will be a second chapter on that. Therefore, I call this symmetry properties 1. So the first one is the so-called intrinsic permutation symmetry. And this intrinsic permutation symmetry is a very abstract or the reasons for this symmetry are very abstract because they can directly be routed back to the response function, to the nonlinear response function. Yeah, so from this you can derive what's called the intrinsic permutation symmetry. Let us just write that down. So the definition of the nonlinear response functions lead to intrinsic permutation symmetry. And now I have to say what it is. So if we have this tensor, specialized here for second order nonlinearities, we introduced already that we write it this way. Yeah, so f minus f3 times f and f, not times. Parameters f3, f1, and f2. Yeah, so if we would up these arguments, then we would get 0. Yeah, so these are not free parameters. These are not free parameters. So the first one depends on the second on this and the third one. So now what is intrinsic permutation symmetry? What it says is that if you change the index here of all parameters but the first. Yeah, so what I say or what I will say does not relate to the first one, but only to the second, third, and perhaps fourth and fifth, and so on. So intrinsic permutation symmetry says that you can flip these two indices if you flip at the same time the respective indices. Yeah, so all of them but the first one. So let me write it down. Yeah, so this is chi I k j, and now minus f3, f2, and f1. So this is intrinsic permutation symmetry. Yeah? And as I said, this is a very fundamental symmetry. It comes directly from the response functions. In the response functions, you can easily show that it holds in the time domain, and you can derive that it carries over to frequency domain. Okay, so this was the first symmetry property. The next one is one that you already know. From the fact that physical quantities and therefore also fields are real, we find that chi of minus f is equal to chi star, complex conjugate, of plus f. All right, so we know that already, so we don't need to discuss it any further. Now, the next one is called full permutation symmetry. Full permutation symmetry means that the restriction I discussed here for intrinsic permutation symmetry, namely that you can't do this game with the first argument and also the first index here, that you now are allowed to do it under, of course, certain conditions. And the condition is that the medium is lossless. So for lossless media, we have full permutation symmetry. Lossless medium, there we have full permutation symmetry. which means that I can, as I said, also flip indices for the first index and the first argument. So I do it for one example here. Namely, I flip the first and the second one. And then, of course, you can go on with intrinsic permutation symmetry and also flip all the others. So we have J, I, K now. And then F1, F3, and F2. Right? Well, and the final one is what's called Kleinman's symmetry. And Kleinman's symmetry is kind of, of trivial, I would say, because it says if we are far off resonances, then we can flip all indices as we wish. Well, which is kind of obvious, because if we are far off resonance, then the susceptibilities hardly depend on the frequency. And if they don't depend on the frequency, then you can apply, of course, the full permutation symmetry as you wish. So far off resonance, this gives rise to Kleinman's symmetry, and it means the indices of high ij can be permutated without a permutation of the arguments. Kleinman was also a physicist, a theoretical physicist with the Bell Labs. I also found his obituary, but it was not as extensive and as interesting as the one for Miller. Okay, so what's next? Symmetry properties 1 was this chapter, and what follows is, of course, symmetry properties 2, namely crystal symmetry. And this is actually a topic that I that I like particularly, because symmetry is always beautiful, but also because it nicely shows how drastically symmetry can affect the properties of a crystal. So crystal symmetry means that if you perform the symmetry on the crystal, say you have fourfold symmetry for a crystal, or let's do it like this. So we have actually just twofold fold symmetry here. So if I rotate that by 180 degrees, and you disregard of the camera here, then you can't distinguish, well, perhaps I should do it this way. So if you rotate it, no, I want to switch it off. So if you rotate it by 180 degrees, it just looks the same. Right? If you do this with a crystal that has the same symmetry, you would have the same thing. So you can't distinguish the crystal after the symmetry operation. And this means, of course, that also the physical properties of this crystal must be the same before and after the symmetry operation. And this can be exploited. And I show it at two examples, one that you already know, and another one that shows how one can proceed. So what does it mean? Yeah, so here I wrote the same what I just said, right? And now we need to know how the susceptibility tensor, how it transforms. Yeah, so when I rotate a crystal, then of course I kind of have rotated also the tensor, and I need to know how this works mathematically. Well, what we need to do is to apply the symmetry operation. So if I have a third rank tensor, then I need to do it 3 times. Right? For you're certainly familiar what you have to do with a second rank tensor. Right? There you would have this just twice, right? And usually one writes it as the rotation matrix, for example, on the left-hand side, and then the tensor that you want to transform, and then on the right-hand side of the tensor, the transposed rotation matrix. Yeah, but in general, we write it in this way, so in the Einstein sum convention. Okay, yeah, and what we demand, so this is the important point here, we demand that the rotated thing, yeah, or that the tensor after the symmetry operation is exactly the same as before doing the symmetry operation. Yeah, so this is what I explained. Okay, let's try that out with inversion symmetry. Yeah, so inversion symmetry means that our symmetry operation is just this thing. Yeah, so we flip the sign of all 3 spatial directions. Okay, and you can write this as the Kronecker symbol. Yeah, and now we apply this. Yeah, so we use this thing here, and for S, we write here this inversion matrix. Right? And I do it here just with the Kronecker symbol, and it is clear that what we get is dijk. Right? -1, so -1 times -1 times -1. Now from 3 times this thing here. Okay, so what we find is that dijk must be equal to minus dijk, right? And this immediately results in the consequence that crystals with inversion symmetries don't exhibit any Xi2 nonlinearities. Yeah? So you see that we have shown it a second time with some perhaps more powerful toolbox. Okay, next we look at crystal class 2. So this is actually this crystal class, I guess. Right, so I said already I can rotate it by 180 degrees through this axis. I can also rotate it by 180 degrees through this axis, yeah, assuming that the back side and the front side is equal. And then there's a final one, namely this axis. Yeah, so I can rotate it by 180 degrees and it still looks the same. Okay, good. Yeah, and these rotations, these 3 rotations by 180 degrees, they are described by these rotation matrices. Yeah, so here, rotation around the x-axis, yeah, so, meaning that the first index remains unchanged, whereas the other 2s are inverted, and so on and so forth. Right? Okay, yeah, and what we have is that we request, so that after the symmetry operation, the tensor is the same, and now the symmetry operation is, for example, this one here. Right? Or if I apply rotation around the y-axis, it's this one here, and the same with the z-axis. Okay, in order to see how this can work, we start with a simple example. Yeah, so we look at a D111, and we say that it must be equal to the rotated D111, and here we have the respective matrices then, right? Well, it is of course clear that that these matrices, in particular also Z, that they only have elements on the diagonal, and so we find here -1, and so we find that D111 is equal to 0. Yeah? Okay, now let's look at the more general case. So we find that Z11 is equal to -1, and this is the same than Z22, whereas this one here is +1. So now if we take the product of these three numbers, then we find a +1, yeah, so that the product is +1 if there are three indices, if there are three indices 3 in this tuple ijk, right, which means that it's 3, 3, 3, right? It is +1 if there's just one 3 in this tuple, so these two, right? And in all other cases, so when there's no 3 or two 3s, then we have -1. So no 3s or two 3s, then we have -1. Okay, yeah? And the immediate consequence of this option here, of this alternative, is that the respective the respective component of the tensor is equal to 0, right? Yeah. So what we do is that we can delete all components, or that we can conclude that all components that contain 2 or 0 3s, that they vanish, right? And we just cross them out, right? And I did it here, right? So this contains no 3, yeah, and this here contains 2 3s. Yeah? So, and we found that then these components are equal to 0. Right? Did the same thing for the second layer of the tensor and the third layer of the tensor. Now we can do the same thing for applying x, right? And then we would say that if we have 2 or 0 ones in this tuple, then we know that this component is also equal to 0. Right? I did it here, right? 2 ones or 0 ones, then these are deleted, and well, you can check it out yourself whether I did it right. And finally, the same thing for y. Then we have no 2 index or 2 indices 2 in this tuple, and we would delete them accordingly, right? And you see that there's only a very limited number of indices, namely a very limited number of components that survives. All the others are 0. So we have 6 non-vanishing, well, at first glance, independent components. It is, however, clear that they are not all independent. For second harmonic generation, we have seen that the last indices permute because you have two equal fields, right? And therefore, it's clear that the last two indices commute. So there are only three independent components. Yeah, and if Kleinman symmetry holds, then there's actually just one independent component. This can be done for all crystals. Of course, we only need to do it for crystals that don't have inversion symmetry. And here you see how this works out. Now, I show these sustainability tensors in contracted notation, right? So you remember this trick to make transform a three-dimensional tensor in a two-dimensional matrix by this trick of contracted notation. So you remember that the sum of these indices should be 9. Well, and now you can look at the different crystal classes. Yeah? So if there's no symmetry, then all 18 components are independent unless there's Kleinman symmetry. Right? So these dashed connections, they mean that these components which are connected, that they are equal. But for class 1, crystal class 1, they are only equal if Kleinman symmetry holds. Right? So the higher the symmetry, the less independent components you have. Right? So uniaxial crystal classes, they are probably the most interesting one. So this is the one that we had so far, right? So you see that we have 3 independent components. If we have Kleinman symmetry, they are all equal. Okay, here it's a little bit more complicated for the uniaxial crystal classes. You also see open symbols. Yeah, so this means that the magnitude of both components is the same, but they have opposite sign, right? And since these lines are solid, this is always the case. For the dashed line, it's only the case if Kleinman symmetry holds. Okay, and finally, we have, besides circles, we have also squares. And this means that they are only non-zero if Kleinman symmetry doesn't hold. Right. Okay, so that's crystal symmetry. So quite important to know which crystal class your nonlinear crystal has, because this determines the number and this determines which components are 0 just because of symmetry. So we are making good progress, I see. Now, the final thing here, I think at least that's the final thing that I wanted to present today. When we introduced the coupled wave equations, then we wrote the nonlinear coefficient we wrote as D effective. And I said at this time, don't worry, this thing here is just connected to the tensor, and I also made a few remarks. So that the idea is to use, instead of these complicated tensor equations, just a scalar equation, right? And so the idea is that if the geometry is fixed, so if the orientation of the crystal is always the same and is predefined, as well as the polarization of the electric fields, then you can write it. Then you can write the nonlinear interaction as a scalar equation, and then of course these tensor components that we just discussed, they are combined in a specific way that reflects this specific choice of geometry, right? And how this works, so how this effective nonlinearity is composed of the components of the susceptibility tensor. This is what I want to show here. Okay, so the effective nonlinearity. Again, for a given fixed geometry, which means that the orientation relative to the direction of the light, including of the wave vector, including and the polarization. So if this is fixed, then the summations in this definition can be carried out, and we get a scalar equation, right? Quite obvious. So here for some frequency and for second harmonic generation, you remember this factor of 2 where it comes from. I don't want to go into this because this was discussed in chapter 2. Now, what we want to do is to derive the effective nonlinearity, and we do it for a specific example, namely for a quartz crystal. Quartz. Let me show it right away. Oh. Well, okay. So quartz is a uniaxial crystal, so it has one optical axis, and what we assume is that both fields co-propagate, propagate in the same direction, which means that the wave vector is equal, right? Then we have, of course, the electric field is perpendicular on K, so it can be in the plane that is defined by K and the optical axis, or it can be perpendicular to that plane. At least we can decompose the electric field in this way, right? And then it is clear that this E double prime is the ordinary ray. It's perpendicular on the optical axis, and therefore the refractive index doesn't change if I change here K. In contrast to E prime, which is the extraordinary beam, because it's not perpendicular to the optical axis, and therefore its refractive index would change if I change the direction of K. Well, but this is not the important point. So, we want to use symmetry class 2-3 quartz, belongs to symmetry class 2-3, and we know that these are the components that are non-zero, right? And you see this reflected here. So this one, this is D11, and this one is the negative of that. Therefore, we have an open symbol here. Right? We don't assume Kleinman symmetry. Otherwise, this component here would be 0, as well as this one here. So they are non-zero here. And you see also this one here is negative as compared to this one here. Of course, you could do this. You don't need to use contracted notation. You can also do it with the kind of three-dimensional notation of this tensor. If you do it in contracted notation, then you also need to write the electric field in contracted notation. And if you go back to chapter 1, then you find that F4, F5, and F6, that they are defined in this way. Right? Okay, so we would plug, so we would use this equation here. And therefore, we can write P1. So P1, so you would multiply this here with F1, F2, F3, so the scalar product of this line with the F vector as a column. Right? And then you get three terms. So D11 times F1 minus T11 times F2. This one here gives 0. Then the next one would be D14 times F2. Right, so you see this here. Yeah, and the same thing, of course, for the second line here. Therefore, we have only two terms, and you find them here, right, with F5 and F6. Yeah, so the last one is, of course, equal to 0. Yeah, so P3 is equal to 0 just because of the structure of the susceptibility tensor for quartz, which is determined by its symmetry. Yeah, 3, 2. Okay, so what we need next is we need the components of E prime and E double prime in the coordinate system of the crystal, because this is here formulated in the coordinate system of the crystal. Okay, yeah, so there's obviously no Z component, so we know immediately that E3 double prime is equal to 0. And for the X component, you can just look at this figure here, and you find immediately that the X component for E double prime, that this is the amplitude times the sinus of theta, where theta is, once again, so this is the plane in which we have the optical axis and the K vector, right? And this one here is the coordinate system of the crystal. So the Z direction is parallel to the optical axis, right? And because this is the ordinary ray here, we found this, that E3 double prime is equal to 0, and we find the X and Y component just by decomposing them using trigonometric functions. Okay, so we did it for E double prime, and now we have to do the same thing for the extraordinary beam. There we have, of course, a Z component. I'm afraid that this should read EZ, well, which is the same thing than E3. Okay, yeah, and then we have, of course, the cosine for this angle phi. So let me, yeah, and theta, you may remember. Right, so theta was this angle, so the angle between K and the optical axis, and phi, once again, so here you see the optical axis and the K vector going through this plane in an inclined way. Therefore, I draw it kind of distorted. Yeah? And so you easily find these components. Yeah? And if you summarize it, if we list what we derived here and what we derived here for the ordinary and the extraordinary beam, then we have these expressions, right? And this we have to insert into equation 13. Well, and this is something to one has to write it down. A little bit cumbersome, makes a little bit of work, but it can be simplified, and we get now this expression here and this expression here. Right? Quite straightforward. So the next point is that we need to go back into the system, into the coordinate system that we're interested in. Yeah, so here we did our calculations in the coordinate system of the crystal, but in the lab the crystal just looks like a piece of glass, right? What you know in the of course, you hopefully have aligned it correctly, but what you, so the coordinate system in the lab, this is the system where you have defined your polarization, right? And so you're interested in the polarization that is parallel and perpendicular to, say, E prime. And then you would find the respective expressions here, in this case for the polarization parallel and perpendicular to E prime. And so these are the two expressions, right? And you would plug in these expressions here, and then you find the final result, so the effective nonlinearity here for the perpendicular direction and here for the parallel direction. Yeah? That's it. Well, and now you have to do this for all crystal classes, at least for, so if you have a specific crystal with a certain symmetry class, then you have to do that analysis for this symmetry. And you can imagine the less symmetric it is, the crystal, the more complicated the expressions will be. But fortunately, this kind of Fleißaufgabe, so this kind of homework was done many years ago by Midwinter and Zernike in their book that I recommended at the beginning of this course. Yeah, I'm done for today. Thanks for your attention, and see you next Monday. Still only online. I hope that in 2 weeks from today I can welcome you here in this classroom again. So thank you again, and have a good week.